right, so my name is Assaf Muller. I'm a Neutron developer. I'm being paid by Red Hat, which is pretty awesome. And as Flavio said, we're hiring, so we're always hiring. So I'm here to talk about Neutron. This is a very kind of broad, I would say shadow, kind of an overview of what is Neutron. Maybe we should have had this talk in the morning, but what can you do? So normally you kind of start with a big graph and you talk about the components and the different networks and all of that stuff, but I'll touch very briefly about the why. What is Neutron even supposed to do? We've already had talks about heat and how does heat create multi-tier networks and all of that stuff, so I'll actually go through this pretty briefly. So the first thing that Neutron we can do is, we've finally we can now provide connectivity between VMs. VMs can now talk to each other. That's pretty great. The other thing that we can do is isolation, right? If you're running a multi-tenant environment, you don't really want the users or the different projects to even know about each other. That's another kind of big goal of Neutron. Other than that, we aim to provide something called network virtualization, which I'll talk about in a second. And the last thing that we do is we've integrated all of the stuff as a service. In the last few releases, we have load balancing, VPN, and firewalls, as been mentioned before. So just a kind of a simple use case, or what can you actually accomplish with Neutron. This is similar to talks that have already happened. So basically, or basically, what is networking virtualization, or at least how I perceive it? So Neutron provides an API, right? And it's a pretty powerful abstraction. So you're now able to just magically create networks via software, right? So if a network was something that, if I consider a network a broadcast domain or some sort of layer 2 networking abstraction, then you can just now say to Neutron, hey, I want a new network, and you've got it. You can create a new network, attach a single or multiple subnets to that network. You can then, right, if we go back to the multi-tier kind of example of a web tier, a logic tier, and a DB tier, then you can create 3 different networks, 3 subnets. You can then define how should these networks talk to each other, if at all. Should they talk to each other? If so, under what conditions? Do I want some sort of filtering on the protocol or the port level? That can be implemented either kind of distributed or centralized via centralized firewall or via security groups, which we'll touch about in a second. So you can group your VMs. You can define the access. You can load balance between them, right? If you're kind of viewing your VMs as workers, then you can create a load balancing service via software, just literally an API call, and then start load balancing your VMs as if they're in a pool. You can provide exterior connectivity, right, via floating IPs, same concept as in Amazon. Just as an idea of what can you actually do. So the base concept, or the basic API, is defined via ports, network, and subnets. And there's actually a lot of kind of talk to, a lot of kind of network purists are saying that this is the right model, and then a lot of application developers are saying this is the completely wrong model. And of course, we're going to have that debate going for a long while. And we actually may change the model in the K version, but for now, and since the Neutron release, we've had ports, networks, and subnets. So a network is a layer 2 broadcast domain, right? I'm going to kind of refrain from using too many networking concepts, but some concepts I just have to use. So we've got networks, we've got ports, whereas a port is an abstraction of a VM's connectivity to a network. So it's kind of the plug point of a VM to a network. So that would mean that a port has a MAC address, an IP address, and it's connected to a specific network. And then we've actually divided the layer 2 and the layer 3 networking into a network model and a subnet model. Whereas like in real life, you can attach more than a single subnet to a network, which doesn't make a whole lot of sense, but it's possible in the physical world, so we've allowed it. So in this specific example, this specific network is realized or implemented via VLAN 10. And I've actually opted to create 2 different subnets over that VLAN, over that network, kind of splitting the subnet space in half. The first 2 ports are connected via the first subnet, and the second port is created via the second subnet. Just as a quick run through of the different concepts. Apart from our models or our API, we've got different types of networks, right? We talked about the network. A network can be realized in very different ways. So I'll go actually kind of the reverse order, or top to bottom. So you've got external networks. External networks are basically networks that have internet connectivity. Provider networks, so then there's the difference between provider and tenant networks. It can be very confusing, mostly because provider networks can be realized or have very different purposes. So provider networks are created only by an administrator. Tenant networks are created only by a user. So kind of thinking about the public cloud use case like HP and Rackspace have. So the administrator would be an employee of Rackspace or HP, and the tenant would be someone like me that I would just register, subscribe, and I have a user and I can create networks and VMs. So provider networks may only be created by administrators, and they serve for one of 2 purposes. So the first purpose is to map to a pre-existing network, as written in the slide. So that means that if my data center has some network, the blue network, which is realized on VLAN 3, so I can now create a Neutron provider network and map it to a specific VLAN. The other usage is to map the provider network to an external network, that type of network. Tenant networks may be created directly by the users. So that's just exposed via the API. I can just, as a user, I can just create my own network and use it for my own purposes. This network would be isolated, of course, from networks of other tenants, of other users of the same cloud. So kind of just talk about the data network, or the network that VMs talk to one another. So just from a networking perspective, how do we do IP addressing and all of that good stuff? So in this specific example, a user created his own tenant network, right? Just through the API, create my own network, create my own subnet, attach them. Awesome. I used Nova. I created a couple of virtual machines, each hosted by a different compute node. And in Neutron, we have this concept of a network node, right? The dreaded network node, which we've worked very hard to eliminate. And have not yet succeeded. So in this specific example, I just created my own network. I decided on my own subnet. Neutron supports overlapping IPs via a lot of magic, and which we'll talk about in a bit. So different networks can actually allocate the exact same subnet, and that's fine. So my VMs can now talk to each other. They probably can't talk to the internet or to other networks. So I actually modeled the external network, right? It's kind of implicit that the network node is supposed to have connectivity both to the OpenStack data network as well as the routable internet external network. So the network node is connected to a new provider network, and this is an actual routable seeder or range. And then I have this new concept of virtual routers. I can just create a router, again via the same API. I created a network, now I can create a router. The router is scheduled on one of the network nodes. In this example, there's one. The router is then attached both to the tenant network, because the router is actually created by the tenant, right? It's a user API, it's not an admin API. So the user created his own network, his own router, chose to attach this router both to the tenant network and to the external network. And now we basically do NAT, right? So if this VM 10.0.0.1 decides to ping Google, then it reaches its own default gateway. The default gateway is realized or implemented as a virtual router inside of the network node. The network node does very basic routing, says, okay, google.com is not hosted on this, on one of my own tenant networks. I'll just forward it out. And the packet is NATed, right? So the source IP address is changed from 10.0.0.1 to this specific IP address, right? 212.10.21. And that packet is then forwarded. So that's good for SourceNAT, right? SNAT, as it's known, the VMs can talk to the outside world. What if normally I use cloud to host my services, and I actually want the people outside of the cloud to reach my servers? So that's the idea of a floating IP. That's basically stolen directly from Amazon. As an elastic IP, I basically attach an external IP to one of my ports, to one of my Neutron ports, for example, this instance. And the network node actually does the NAT in the reverse order. Okay, so I actually don't have a lot of time, so I'll probably choose to skip the least important bit. I guess that's how it's normally done. So let's just kind of have a brief overview of the different components. So first off, there's a lot of information in the slide. There's 4 different networks. This is kind of the ideal situation. You could have a single physical network and just partition it via VLANs, but here, for this specific example, we're using 4 different physical networks. So the VM data, the teal network, we've already talked about. The orange network, if that's orange, is the management network, so the different services, all of the different API calls, or all of the different notifications, that sort of stuff is realized via the management network. Then you've got the network node, of course, has to be connected both to the internet, as well as the API node, the node which is hosting the Neutron API service at the bare minimum, probably also the Nova Horizon and so on, different services, also has to obviously have external connectivity via the API network. So let's talk about the different components. The Neutron components are in bold. So the first component, the Neutron component itself, sometimes you place it on the API node, sometimes you place it on the network node. But basically this service is the guy that is accepting API requests. So it's getting create network, create port, create subnet, create router from the outside world, persists it in the database, and then sends out notifications, which we'll talk about in a minute. You've got layer 3 agent, DHCP agent, metadata agent on the network node. A lot of that stuff realizes the different API calls. For example, create router, as we've said before, is received by the network node, persisted to the database, which is on some other node. A message is then sent via the AMQP broker, received by the network node. The layer 3 agent receives the message, goes, okay, someone wanted to create a new router, I'll create a new namespace, right, a Linux namespace. Just an implementation detail of a virtual router. The virtual router is then created. The DHCP agent, we probably want to provision IP addresses for our virtual machines. So whenever Nova creates a bunch of virtual machines, calls out to Neutron, Neutron creates ports, which we've talked about earlier. The create port command is received by the network, by the API node, persisted to the database, notification sent to the DHCP agent. DHCP agent then brings up a DNS mask process. So a DNS map process is one way in Linux of creating a DHCP server. So we basically create a DHCP server for a network. The notifications are received by the DHCP agent, which then has a lease file, right? Like any DHCP server, it goes, okay, so you want to provide DHCP services for 10.0.0.1 with MAC address, blah. So that's received via notification by the DHCP server, which basically writes it to a lease file. So that we basically make sure that whenever a VM boots up, sends a DHCP request, that's eventually received by the DHCP agent, which can reply. Metadata agent, basically provide services for cloud init, that sort of stuff. the metadata agent is actually just a proxy. It just basically receives the metadata queries and sends it forward to the Nova database, which actually persists and holds all of the metadata for each instance. So you should be kind of thinking about why is that? There's no reason to proxy this stuff unless there is a reason. So there is one, and that's because of overlapping IPs. Nova doesn't have the concept of overlapping IPs. Nova perceives the world as, every VM has a unique IP address, and that's not the case if you're not using Nova Network and you chose to use Neutron. So the proxy basically goes, okay, I have this information in the header, I know which VM is it, and then I basically make a couple of API calls and place the instance ID in the headers. That's forwarded to Nova, so Nova now has the instance ID, which is a unique identifier for each instance, and the IP address isn't. Then you're left with the layer 2 agents. So a layer 2 agent is placed on every compute node, as well as the network node. The layer 2 agent actually provides layer 2 connectivity or wiring. So whenever a VM is scheduled on this node, it goes up. Nova basically calls out to Neutron, goes, Neutron, please create a port on some network, which was pre-specified. That's received by the network. Neutron API node persisted to the database, sends a notification to the layer 2 agent, to the correct layer 2 agent, which then goes, oh, okay. So you want to provide network connectivity for a port with a specific MAC address, specific IP address, which is also supposed to be on some network. Well, I can do that. Normally, kind of the default, if there is a default, layer 2 agent is realized via Open vSwitch, Open Virtual Switch, which the layer 2 agent then basically configures the flow tables on the Open vSwitch, basically going, okay, so this tap device belonging to this VM is now allowed to talk on VLAN 20, for example. So it basically does the connectivity, providing access from a VM to a VLAN, or you can realize or implement tenant networks not via VLANs, but with tunnels, right? With GRE and VXLAN tunnels, which I'll mention in a bit. We've been through that. So another example, which kind of should help realize the idea of what each different component does. I think a good example is the way that Nova creates a VM. So the communications between Nova and Neutron can be slightly problematic. There's been a lot of bugs that are, kind of, the networking doesn't work. Everyone immediately blame Neutron, but sometimes it's not Neutron's fault. Sometimes it's actually, kind of the glue code, which doesn't really work properly. And this would be a great example. This is actually an example following the icehouse cycle, which actually fixed a lot of stuff, and the situation is still kind of weird, which you will now see. But this is a good example of what each different component actually does. So Nova gets an API call to create a VM, then basically passes it along to a different Nova service, schedules the VM, chooses a host, then sends an RPC notification to the compute node on the left host. The left host goes, oh, okay, you want to create a new VM? Sure, I can now create a new Neutron port, as well as create a tap device. Tap device is the Linux way of kind of hooking up a VM to the network. Neutron goes, okay, I got your API call. I'll allocate a MAC address and an IP address on the network that you wanted. Notifies both the DHCP agent and the layer 2 agent, right? Notifies the DHCP agent because it needs to update the lease file, so it can then provide DHCP answers. Notifies the layer 2 agent, so it can provide the connectivity that we talked about a moment ago. The compute node then goes, the layer 2 agent goes, okay, I understand that you want me to provide connectivity, but I need to ask you for some more information. That should raise a few eyebrows. Asks for more information, gets a reply, configures the local VLAN, sends this is a new icehouse addition, sends a new port up notification, received by Neutron, sent to Nova. Nova then, I actually lost myself. Nova then goes, okay, so the port is now ready, right? The port is now wired, you should have connectivity. Sends that back to the compute node. There's a big question of why can't Neutron and Nova just talk here, but whatever. Nova receives that information, the port is now up, it's ready, it's wired, start the VM. Yeah, this is a big example of OpenStack complexity. Finally, just kind of as a quick summary, everything that I've just said is partially a big lie. The reason is, of course, like many other projects, Neutron is very pluggable. So the implementation of the API is completely different depending on the plugin that you chose. I assume that we're using the default plugin, which is ML2 with OpenVSwitch, which we spend a lot of time, which we work on a lot. There's a lot of different plugins. Some are certified by Red Hat, but that shouldn't matter. So some plugins actually just receive the API call and then persist it to the database or not, then just proxy the call to some other server, which does the actual work, like OpenDaylight and nearly all of the plugins actually. So this is kind of an important bit to remember, where the OpenVSwitch agent, for example, may or may not exist. Completely depends on the plugin that you chose. Finally, we haven't touched the service plugin, and we won't. Firewall, VPN, load balancer, good stuff. Neutron does it. Finally, we haven't discussed how do we actually do connectivity and isolation between different networks, right? We've touched briefly about VLANs and tunnels. So luckily, I already gave this talk, so shameless plug. There's a video and a very lengthy and blog post basically detailing exactly how does it work. So you can learn whichever way you're comfortable with. Just Google my name on Google. That's about it. We don't have time for questions. I'm always available on IRC and emails, and I love to talk about this stuff, so talk to me whenever. Thank you.